In 1997, Leonard Susskind made a bet with Stephen Hawking. The stakes, an encyclopedia. The question, does information that falls into a black hole get destroyed forever, or does it somehow survive? Hawking said it's gone, erased from the universe. Susskind said that's impossible. It would shatter the foundations of quantum mechanics. For 7 more years, they battled it out. Papers, conferences, public debates. And then in 2004, at a conference in Dublin, Hawking stood up in front of the entire physics community and conceded he'd been wrong. Susskind had won. This is the story of the Black Hole War, one of the most dramatic scientific battles of the 21st century. To understand why this matters, you need to know one thing about Leonard Susskind. He doesn't back down. Born in 1940 in the South Bronx, Susskind grew up in a working-class family. His father was a plumber. Nobody in his family had ever gone to college, but his father had a dream for him. As Susskind recounts in his book, The Black Hole War, his father once told him, "You ain't going to be no engineer. You're going to be Einstein." And in a way, that's exactly what happened. By the 1990s, Susskind had already made his mark on physics. He'd co-discovered string theory in 1970. He'd helped develop the holographic principle, the idea that our 3-dimensional universe might actually be encoded on a 2-dimensional surface. He was a professor at Stanford, respected but not exactly a household name, not like Stephen Hawking. Stephen Hawking, by contrast, was the most famous scientist on the planet. The Wheelchair, The Computer Voice, A Brief History of Time, which sold over 10 million copies. When Hawking spoke, the world listened, including the physics community, and in 1976, Hawking had made a claim that shook physics to its core. He'd proven, using the mathematics of quantum field theory in curved spacetime, that black holes aren't actually black, they glow. They emit radiation, thermal radiation, now called Hawking radiation, and that radiation is completely random. It carries no information about what fell into the black hole, which means, according to Hawking's calculation, information is destroyed. Now, that might not sound like a big deal, information, who cares? But here's why it matters. The destruction of information violates one of the most fundamental principles in quantum mechanics. In quantum mechanics, information is always conserved. If you know the exact state of a system now, you can in principle work backward or forward to figure out what it was or what it will be. Past, present, and future are all connected through the equations. Nothing is ever truly lost. But black holes, according to Hawking, break that rule. Throw a book into a black hole. Wait for it to evaporate via Hawking radiation. The book is gone, the information in it, the arrangement of atoms, the words on the pages, everything is destroyed, gone forever. If Hawking was right, quantum mechanics was broken, and we'd need a new physics. Susskind didn't buy it. Let's set the stage. It's 1983. Susskind is at a physics conference in San Francisco. Stephen Hawking is there, giving a talk about his black hole radiation work, and Hawking makes his claim information is destroyed in black holes. Quantum mechanics fails. Susskind is sitting in the audience, and as he later described it in The Black Hole War, his immediate reaction was, "That can't be right." After the talk, Susskind approached Hawking. He tried to explain why information must be preserved. Hawking wasn't interested. In his computer-generated voice, he told Susskind he was wrong. The conversation ended there, but Susskind couldn't let it go. Here's the thing nobody tells you about black holes. They're simple, incredibly simple. John Wheeler, the physicist who coined the term black hole, once said, "Black holes have no hair." What he meant was a black hole is described by just 3 numbers: its mass, its electric charge, and its spin. That's it. Nothing else matters. You could throw an encyclopedia into a black hole, or a pile of random junk. As long as they have the same mass, charge, and spin, you get the exact same black hole. So when a black hole evaporates via Hawking radiation, all you're left with is thermal radiation, heat, random photons carrying no information about what went in. The encyclopedia and the junk produce identical radiation. That's Hawking's argument. And mathematically it was airtight. His calculation was correct. The radiation is thermal. It's random. But Susskind saw a deeper problem. If information is destroyed in black holes, then the whole framework of quantum mechanics collapses. Here's why. Imagine you have a quantum system, say, a collection of particles in a box. In quantum mechanics, that system has a state. You can describe it with something called a wave function. And as time passes, the wave function evolves. The evolution is deterministic, meaning if you know the wave function now, you can calculate what it was in the past or what it will be in the future. The information is always there. But if black holes destroy information, then you could start with a pure quantum state, throw it into a black hole, wait for the black hole to evaporate, and end up with thermal radiation, which is a mixed state, not a pure state. You've gone from a pure state to a mixed state. That's a violation of quantum mechanics. It means the laws of quantum mechanics don't work anymore. Think about that for a second. Quantum mechanics is the most successful theory in physics. It explains chemistry. It explains the behavior of atoms, electrons, photons. It's the foundation of all modern technology. Computers, lasers, MRI machines. If quantum mechanics breaks down around black holes, then we don't understand the universe at all. Susskind wasn't willing to accept that. He believed quantum mechanics must be more fundamental than our understanding of black holes. The information must survive somehow. He just didn't know how. And so for the next decade, Susskind thought about the problem. He talked to other physicists. He read Hawking's papers over and over, looking for a loophole. And then, in 1993, he found one. The breakthrough came from an unexpected place, a conversation with Gerard Hooft. Gerard Hooft is a Dutch theoretical physicist, Nobel Prize winner, brilliant, iconoclastic, unafraid to challenge conventional wisdom. And in the early 1990s, Hooft had been thinking about the same problem Susskind was obsessed with. In 1993, Susskind and Hooft were both at a workshop in Santa Barbara, the Kavli Institute for Theoretical Physics. Hawking was there too, presenting his latest work on black hole information. And after Hawking's talk, Hooft pulled Susskind aside in the hallway. As Susskind recounts in The Black Hole War, Hooft told him, "Stephen is wrong about this, but I don't know how to prove it." That conversation was the spark. Over the next few months, Susskind and Hooft exchanged ideas. They met at conferences, they scribbled on napkins over dinner, and slowly a radical idea began to take shape. What if the resolution to the information paradox wasn't about changing quantum mechanics or changing general relativity? What if it was about changing our perspective? Here's the idea Susskind proposed in a 1993 paper with L. Thorlacius and J. Uglum. It's called black hole complementarity. The core insight is this: there are two different descriptions of what happens when something falls into a black hole, and both descriptions are correct, but no single observer can see both at the same time. Let's break that down. Description 1: scene. The perspective of someone falling into the black hole. You cross the event horizon. Nothing dramatic happens. The horizon isn't a physical surface. It's just a boundary in space-time. You pass through it smoothly. You don't feel anything special. You keep falling toward the singularity at the center. From your point of view, you carry the information with you. It's not destroyed. It's just inside the black hole with you. Description 2: the perspective of someone watching from outside. From the outside, you never actually see the infalling object cross the horizon. Due to gravitational time dilation, as the object gets closer to the horizon, time slows down. The object appears to freeze at the horizon, getting dimmer and redder, eventually fading from view. But here's the key. From the outside observer's perspective, the information from the infalling object gets encoded in the Hawking radiation that eventually comes out. Two descriptions. One says the information goes inside. One says it comes back out. Now here's where it gets wild. Susskind's proposal was both are true. But there's no contradiction because no single observer can verify both descriptions. If you fall in, you can't get back out to check that the information was also in the radiation. If you stay outside, you can never go in to check that the information was also inside. The two perspectives are complementary, like in quantum mechanics, where a particle can be described as a wave or a particle, but you can't measure both aspects simultaneously. This was a radical idea. It meant that physical reality depends on the observer, not in some mystical sense, but in a precise, mathematical way. Black hole complementarity said information is both destroyed and preserved, depending on who's looking. When Susskind presented this idea at conferences, reactions were mixed. Some physicists thought it was brilliant. Others thought it was insane. How can information be in two places at once? How can both descriptions be true? But Susskind had an answer. He argued that the apparent contradiction is resolved by the fact that the two descriptions can never be compared by a single observer. And in physics, if something can't be measured even in principle, it's not a real contradiction. Ade Witten, widely considered the smartest person in theoretical physics, sat in the front row during one of Susskind's talks on this. According to Susskind, Witten had this look on his face, like he was trying to figure out if Susskind was crazy or brilliant. But there was a problem. Complementarity was a proposal, not a proof. It told you that information could be preserved, but it didn't tell you how. What was the mechanism? How does information actually escape from a black hole? Susskind didn't have the full answer yet, but he had something else, confidence that Hawking was wrong, and that's when he made the bet. The bet was public, made in 1997 at another physics conference. Susskind and two other physicists, John Preskill and Kip Thorne, made a bet with Stephen Hawking. The stakes, a baseball encyclopedia. The terms were clear. Does information get destroyed in black holes, or is it preserved? Hawking bet that it's destroyed. Susskind, Preskill, and Thorne bet that it's preserved. And for the next 7 years, the battle raged on. Hawking wasn't backing down. In 1997, he published a paper doubling down on his position. He argued that black hole evaporation is fundamentally non-unitary, meaning it doesn't preserve quantum information. He acknowledged the complementarity idea but dismissed it. The math, he said, was clear. Susskind fired back. In 1998, he published more papers on complementarity and started developing another idea, the holographic principle. If information is encoded on the surface of a black hole, on the event horizon, then maybe it never really falls inside at all. Maybe everything inside the black hole is actually a holographic projection of information stored on the horizon. This was the idea that would eventually become the foundation of modern string theory. But in the late 1990s, it was still controversial. String theorists were starting to get excited about it, especially after Juan Maldesena's groundbreaking work on ADS-CFT correspondence in 1997. But it wasn't yet clear how it solved the black hole information problem. Meanwhile, Hawking kept pushing back. At conferences, the two men debated. It was always respectful. Susskind admired Hawking, but it was intense. The stakes were enormous. This wasn't just about one problem. This was about the consistency of physics itself. Then, in the early 2000s, new ideas started emerging from the string theory community. String theorists started calculating. They could describe black holes as bound states of strings and brains. And when they did the calculations carefully, they found that the microscopic entropy, the count of quantum states, matched the Bekenstein-Hawking entropy exactly. That meant black holes really were quantum mechanical objects, and quantum mechanical objects don't destroy information. Hawking started to waver. In 2003, he gave a talk at Cambridge where he admitted that black hole complementarity might be right. He still wasn't convinced, but he acknowledged it was a possibility. And then came Dublin, July 2004. The GR17 conference, one of the biggest general relativity conferences in the world. Hundreds of physicists gathered in Ireland, and Hawking announced he was giving a surprise talk. The auditorium was packed. Everyone knew what was coming. Hawking stood before the crowd, sitting in his wheelchair, his computer voice ready, and he said it. I was wrong. He explained that he'd been thinking about the problem more carefully. He'd realized that information must be preserved. The details were still unclear, but the principle was right. Quantum mechanics wins. Information doesn't get destroyed. Susskind was in the audience, and as he later wrote in The Black Hole War, it was one of the most gratifying moments of his career. Hawking had conceded. After the talk, Hawking approached Preskill and handed him a baseball encyclopedia, payment for the bet. Thorne, interestingly, didn't accept his share of the prize. He said he wasn't yet fully convinced the problem was solved, but Susskind celebrated. He'd won the Black Hole War. Now, here's the thing. Hawking's concession didn't end the debate, it shifted it. Physicists still argue about how exactly information escapes from black holes. The mechanism isn't fully understood, but the principle that information must be preserved is now almost universally accepted. Hawking's 2004 concession was based on an argument involving topology of spacetimes and wormholes. It wasn't the most detailed proof, and some physicists criticized it as incomplete, but it was enough. Hawking admitted that his original claim, that information is destroyed, was wrong, and that shifted the entire field. Today, black hole information preservation is a cornerstone of modern theoretical physics. It's connected to some of the deepest ideas in string theory, quantum gravity, and the holographic principle. But in 1983, when Susskind first stood up to Hawking, almost nobody believed him. It took 28 years. So what does all of this actually mean? Why does it matter that information escapes from black holes? Here's the thing. The black hole information paradox wasn't just about black holes, it was about the foundations of reality. If information had been destroyed in black holes, it would have meant that quantum mechanics, the theory that explains atoms, chemistry, electronics, everything in the quantum world, was incomplete. We would have needed a new theory, a theory that allows information to be destroyed. But because information is preserved, quantum mechanics survives. It's still the foundation of physics. That's enormous. But there's more. The resolution to the information paradox led to one of the most beautiful ideas in modern physics, the holographic principle. Here's the idea, which Susskind developed in his 1994 paper, The World As A Hologram. If you want to describe everything that happens inside a black hole, you don't need to keep track of all the information in the three-dimensional volume. You only need to keep track of the information on the two-dimensional surface, the event horizon. It's like a hologram. A hologram is a two-dimensional surface that encodes a three-dimensional image. Shine a laser through it, and you see a 3D object, but the information is actually stored on the 2D surface. Susskind proposed that the same thing is true for the universe. Everything that happens in three-dimensional space is actually encoded on a two-dimensional boundary. The universe is a hologram. That sounds insane. And honestly, it probably is insane, but it's also supported by some of the deepest mathematics in string theory. In 1997, Juan Maldacena, a physicist at the Institute for Advanced Study, proved a version of this idea in the context of anti-de Sitter space. It's called the Addis-CFT correspondence. It says that a theory of gravity in a certain kind of curved spacetime is exactly equivalent to a quantum field theory on the boundary of that spacetime. Three-dimensional gravity to two-dimensional quantum field theory. It's one of the most important discoveries in theoretical physics in the last 30 years, and it grew directly out of the ideas Susskind developed while battling Hawking. But the implications go even further. If the holographic principle is true, it means our intuition about space is wrong. We think of space as three-dimensional, left, right, forward, backward, up, down. But the holographic principle says that's an illusion. The fundamental description of reality is two-dimensional. Three-dimensional space is emergent. It's a projection, a hologram. Your body, this room, the earth, the stars, all of it might be a holographic image projected from some distant two-dimensional surface. Think about that for a second. If that doesn't blow your mind, I don't know what will. Today, Susskind is still working on these ideas. He's in his mid-80s now, and he's still publishing papers. In recent years, he's been focused on something called quantum complexity, the idea that the interior of a black hole continues to evolve long after it looks like nothing is changing from the outside. The complexity of the quantum state inside keeps growing, even when the entropy has maxed out. This connects to another major research program, understanding holography in de Sitter space, the kind of space-time that describes our actual universe. Susskind has been collaborating with Edgar Shagalian, Adil Rahman, and others on this problem. It's much harder than Ada's CFT because our universe is expanding, not contracting. But if they figure it out, it could be the key to understanding the quantum nature of our cosmos. And it all traces back to that moment in 1983 when Susskind stood up at a conference and told Stephen Hawking, "You're wrong." Leonard Susskind is 86 years old now. He's been doing physics for more than 5 decades. He's co-discovered string theory. He invented the holographic principle. He fought a 28-year battle with the most famous physicist in the world and won. But here's the thing that strikes me most about this story. It's not just about being right, it's about persistence. In 1983, almost nobody believed Susskind. Hawking was a superstar. Susskind was just a professor at Stanford. Hawking had the equations. Susskind had a hunch. But Susskind didn't give up. He kept thinking. He kept working. He kept pushing back, even when it felt like the whole physics community was against him. And eventually, the evidence caught up to his intuition. There's a lesson in that, not just for physicists, but for anyone. The universe doesn't care how famous you are. It doesn't care how many equations you have on your side. It cares about what's true. And sometimes figuring out what's true takes decades. Susskind is still publishing papers, still teaching at Stanford, still asking questions that make the rest of the physics world uncomfortable. If you want to understand quantum mechanics and general relativity, you have to understand complementarity. If you want to understand string theory, you have to understand the holographic principle. And if you want to understand why we believe information can't be destroyed, you have to understand the black hole war. This is Leonard Susskind's legacy, and the story is far from over. Next time, we'll talk about the holographic principle in detail, the idea that our three-dimensional universe is actually a projection from 2 dimensions. Because if Susskind is right about that, reality is far stranger than anyone imagined.